we have question number 2. Let ABCD be a cyclic quadrilateral whose diagonals intersect at here. Suppose AB is equal to 9, CD is equal to 9, AD equals 16, and AC bisects BAD. Find AC plus BD. Okay, I will draw a figure here. Just wait. Just to actually no. I'll draw a figure here just to like make the viewing it like make it a bit easier, but to like visualize. But yeah, does anybody have any thoughts on how to approach this problem while I'm drawing the figure? Like, okay. So, by the way, for geometry diagrams, it's usually very helpful to like um draw them nicely because it makes finding the angles a lot easier. I'm finding the oh yeah, sorry, forgot. Um, a cyclic quadrilateral basically is a quadrilateral that can be inscribed in a circle. So in this case, it would look something like this. I'm sorry, bad at drawing circles, but you kind of get the point. Like this. Yeah, it's a good drawing. So, oh, sorry, Andrew, I didn't read your message. So you can use the bisected angle to find the other length because they have people. Uh, yes, actually. So, um, for this problem, notice since they're inscribed in a cyclic quadrilateral. I'm sorry, sorry. Since B CAD subtends arc CD and the angle BAC subtends angle arc BC, right? And since sorry, an arc subtended by an angle must be twice that of an angle, right? So this is known as the, if I remember correctly, um, yeah, actually, it's a well-known fact that when angle sub is inscribed in a circle, that the arc subtended by the angle is um twice that angle. Yeah, basically. So for example, if I have an angle ABC, this arc right here has angle X, right? I'm sorry, has um arc length. It's arc length and arc it has arc angle 2x. So in this case, since these angles are equal, we know since these arcs must also be equal. So this must be equal to this, right? And we can use it to find the other length. Okay, but how do we? What must be constructed to find the other length? So, also, sorry, it's a bit misleading, but anyways. So, does anybody have any um tip? Like, does have any ideas on how to find the other length, which is BC, yeah, in this case? So, equal arcs towards. Yes, actually. Wait. Yeah, yes. They're actually right. Um, this is true. But what I was actually planning was for um to kind of prove this. It's like construct triangle BCD, yeah. Sorry for my bad drawing. And then realize since these subtend equal arcs, these angles must be equal. And in fact, since these angles subtend the same arc, they also must be equal. So all these four angles right here are equal. But that for the for this, it doesn't really matter because we can now find other length for BC because since these angles are equal, these sides must also be equal, which means this side length must also be 9. Now we still need to find AC plus BD, right? So how do we find how do we relate how do we use this information to find AC and BD? Actually, I'll give you a better question. Um, is there any relation between AC and BD? Yeah? Yep, Andrew, you're right. Okay, so Ptolemy's in this case is referring to Ptolemy's theorem, where if there's an sorry if there's an if there's a cyclic quadrilateral ABCD, then AB plus sorry yeah um AB times CD plus AD times BC is the equal to the product of their diagonals. So sorry, plus AD times BC is equal to the product of their diagonals. So that is AC times BD. Now, I'm not going to go more in depth into this, but you can research about the Ptolemy theorem. Ptolemy theorem. I think that's the name. I think I might have misspelled it, but okay. But this theorem helps us find the product of the diagonals. But how do we use this information? Well, actually, wait. This information will actually be used for later. So notice that 80 times BC is equal to 16 times 9, which is 144, right? Plus 89 times 9, AB times CD, which is 81, is equal to um, AC times BD, which means that 25 is equal to the product of AC times AC and BD, right? Now, Um, Andrew, you also said it's an isosceles trapezoid, right? That is true, actually. Again, what I was planning here was for congruence, for triangle congruence, but basically um we can prove that AC is equal to BD, yeah, through realizing that it's an isosceles trapezoid. Since it has to be a bit more rigorous, but since um this next um since this angle here is equal to this angle here by some angle chasing with us arcs, but also we can see that since AB is equal to BC equal to CD, right? Is equal to 9, right? Um, and we know that the angle CAB is equal to angle BCA, which is equal to angle BC, which is equal to angle BDC. Basically, yeah, we can prove by angle side or AAS or um FES or yeah, basically almost all we can prove using all the congruences that um triangle ABC is congruent to triangle DCB. For this case, we can show it by AAS since angle CAB is equal to angle ACB, which is equal to angle DBC, which is equal to angle BDC, and since AB, again, since AB is equal to BC equals CD equals 9, right? So therefore, we can show that AC is equal to BD. And lastly, we can finish this off by realizing, yeah, by the way, we want to find AC plus BD here, which is basically equivalent to AC here, since we know that AC is equal to BD now. But basically, we can just substitute in AC is equal to BD here in AC times BD, and we get that AC squared is equal to 225, and we can just immediately concluded from that AC is equal to 15, because of course a side length can't be a negative number. So therefore, since AC we just need to find 2AC, we know that our answer 2AC is 30, and that is our answer. So does anybody have any questions? Oh yeah. By the way, just like a side note here, you can also prove this using law of cosines and a lot of bashing, but it's very yeah, it's not particularly the most efficient way to do the problem because you're gonna have to like do a lot of algebra. So here is a more synthetic, but in other words, it's like use the normal geometric we use as little algebra as possible for our problem. The synthetic ways.